Hello, Chemistry 2330. Today we're going to talk about Chapter 11, Spectroscopy. So the first thing we want to talk about when we talk about spectroscopy is the idea of electromagnetic radiation. Okay, so electromagnetic radiation is light and other forms of radiant energy. And as the name implies, there's an electric component to it and a magnetic component to it. So this electric and magnetic components of light can interact with molecules and other matter to give us an insight about what kind of bonds or atoms we might have. Okay, so when we talk about electromagnetic radiation, the first thing we want to talk about is wavelength. Okay, so the wavelength is the distance between two consecutive points in a wave. So if we have a wave that's going like this, the wavelength is from any two of the same positions, that distance there. So that's our wavelength from those things. And it's signified by the symbol lambda, okay? So if we talk about how many cycles it takes to go in 1 second, right here, that's called frequency. So the number of full cycles per second of a unit, then that equals frequency. And that is our symbolized by our symbol nu. Okay. Most of the time when we talk about frequency, we use it in the term of hertz. Hertz is in the unit of per second. So that means how many waves per second happen there gives us that frequency, and it's in the unit of hertz. Okay. So if we look at that again, we can see that these are some common units that we have for a wavelength. We can do millimeters, micrometers, nanometers, or angstroms. We'll be using our own one called reciprocal centimeters that we're going to be using. Okay, so if we think about the entire range of the electromagnetic spectrum here, we only see with our eyes a very small amount, and that's the visible light section here, this little teeny section where we can get all of our red, green, blue, and violet right here. But on either side of that, there are longer wavelengths, which include the infrared, microwave, and radio waves. And then there are shorter wavelengths, which is UV light, X-rays, and gamma rays. And so what we see with our eyes is only at that little small section. What we're going to be looking at is these infrared, which are longer than visible wavelengths, and some of the radio waves and how they interact. These interact with different bonds lengths, and these interact with the nuclei of the different atoms. Okay, so when we talk about that as spectroscopy, we're saying these different forms of electromagnetic energy react with different molecules, okay, and different bonds. And so the entire range is called molecular spectroscopy. So it's the study of all the different frequencies which interact with matter. So we have two main types that we'll be using here. The first we're looking at is infrared spectroscopy. And what that does is that's looking at the vibration whole energy between two atoms and how it does and how that interacts with that light. The second thing we're going to look at is the radio frequency. The radio frequency affects the spin of the nucleus. So a nucleus, just like a planet or a sun, has a certain spin associated with it. And by taking that spin and flipping it back and forth, we can see that with radio frequencies. Okay, so let's talk about how this interacts. Okay, so the way this interacts is the energy of the wave is absorbed, exciting the molecule, the atom, or the bond by absorbing that energy and taking it into a higher state. Okay, so the energy it took to convert it to the higher state is our difference in energy, and therefore we can take those differences in energy and equate them to different molecular structures. Okay. So in infrared spectroscopy, though, that's the spectroscopy that's just below the wavelengths of visible light here. We look at that range that extends from 2 to the minus 6 meters to the minus 5 meters, okay? Now, because that's a really hard number to look at, we actually converted that into what we call wave numbers, or this is reciprocal centimeters. So whenever we look at an IR spectrum, what we're going to see is that the numbers at the bottom of the screen are going to go from 400 reciprocal centimeters to 4,000 reciprocal centimeters to 400 reciprocal centimeters. And that equates to this entire range available to us here. So when we look at a spectrum, the common spectrum would look something like this. We would have our 4,000 range down here, going all the way up to 400 here. So these different bands in the IR equate to different types of functional groups. And so different areas in the spectrum will show up with different functional groups. And I'll show you different little things to look for in each of those systems. So when we're talking about IR spectroscopy, we're looking at molecular vibrations, okay? So the vibration between two different atoms or between multiple atoms gives us that energy that is absorbed from that light. And so if it's absorbed from the light, we're taking it away from the system. And therefore, what we see is that here we have 100% of the light of this energy being transferred through the system, but most of the energy, most of the light in this band is actually being absorbed. And then almost none of the light's being absorbed in this area and more is being absorbed in these areas. So we can think of is that each of those peaks associates with, oh, there's something that is absorbing light and vibrating. Okay. And so the difference that can be absorbed actually gives us a difference in the intensity of these peaks. Okay, so for a bond to absorb IR radiation, the frequency must match the frequency of the bond vibration, okay? So the bond has to vibrate, but it also must be polar. So non-polar bonds have very weak absorptions in IR. So we're looking for polar bonds that tend to be the differences between multiple atoms, or they have different electronegativities on them. So if we look at the multiple bonds within within these systems here, we're seeing there's a whole bunch of carbon-carbon bonds and carbon-carbon double bonds. Well, there's very little vibration in these, and so that these tend to be IR inactive, or they do not absorb because they are non-polar, and therefore they don't interact with the vibration. So what we're looking for is differences between atoms of different electronegativity, and that give us the best vibrations that can be seen by IR. Okay, so now it doesn't just have to vibrate between two atoms. We also have different fundamental vibration modes. You don't have to know all these. I just want to introduce the topic that we can have things where a total of, like this top one here is where we have the hydrogens are stretching symmetrically away from each other, and that's a certain vibration. They can also unsymmetrically stretch like this and give us a different vibration. There's also wagging and individual atom vibrations. Each of these different modes shows up in a different energy and shows up in a different band of the IR spectroscopy. Okay, but what I want you to focus on is looking at where the different regions are and what they should be found in. Okay, so these are the 4 bands of IR you should be familiar with. First band here is this upper band between 4,000 and 2,500 wave numbers here. This is a big atom with a small atom, and therefore it has a high frequency that it vibrates at, and it's a high energy frequency, okay? So these light atoms vibrate at a higher frequency and therefore have a higher energy. So think of it as a heavy atom with a small atom giving us this bond. And so all of our CH stretches will be there, all of our OH stretches will be there, and all of our NH stretches will be there. Okay. The next band to look at is between 2,500 and 2,000. That's where we have carbon-carbon triple bonds and carbon-nitrogen triple bonds. So these are really tightly bound together. Again, they're a very strong bond, and so they're vibrating at a high frequency, but they're not the same because it's two heavier atoms. It's not in the same band that these lower ones in. It has their own band. So it's a little bit less energy than that big atom, small atom, but they are very well bonded together. So you think triple bonds, that's a very high energy. The next band we need to look at is the 2000 to 1500 wave number area. This is where we find our carbon-carbon double bond, our carbon-oxygen double bond, and our carbon-nitrogen double bond. Again, we have two bonds there. It's very tightly bound, but not as tightly bound as a triple bond, and more tightly bound than a single bond on this side. So they're going to vibrate at a slightly higher energy than a single bond, but at a lower energy than a triple bond. So that's why they're found in this middle region. This is where we find a lot of our ketones and our aldehydes and other bonds. So our last one is our zone under 1500 down to 400. This is where we find our heavy atom single bonds. So our carbon-carbon single bond, carbon-oxygen single bond, carbon-nitrogen single bond, and our carbon halide single bonds. All of those single bonds take place down in this, what we call the fingerprint region, okay? So that being said, we look at the relative intensity of things absorb, okay? So when we look at the relative intensity of things absorbing, the more polar the bond is, the more it's going to absorb, okay? So in the case of, for example, the OH, that's a very polar bond, so we're gonna have an intense absorption in it. The carbon-nitrogen bond is going to be the next most polar bond, and therefore it's going to have the next most intensity. And then the carbon-hydrogen bond is the least polar in this set, and therefore it's going to have the lowest intensity available to it.